Hello, this is Bryant Myers, author of PEMF, the Fifth Element of Health, and I'm excited about this video because we're going to look at Maxwell's equations, and we're going to see that they summarize everything we've learned about in this course. In fact, they summarize everything electrical, magnetic, and electromagnetic, including light. So let's get right into it. Maxwell's equations are the four most influential equations in science: Gauss's law for electric fields, Gauss's law for magnetic fields, Faraday's law, and the Ampere-Maxwell law, all of which we have seen in simpler forms in earlier modules. If you need testament of Maxwell's equations, look around you. Radio, television, smartphones, radar, computers, wireless internet access, and Bluetooth technology are a few examples of contemporary technology that's rooted in Maxwell's electromagnetic field theory and these four equations. So it's little wonder that the readers of Physics World selected Maxwell's equations as the most important equations of all time. And for our purposes, these four equations, along with the Lorentz force law, contain all the physics needed to understand PEMF devices and, in fact, most energy medicine devices as well. So now let's go through each one very briefly. We'll stick with the integral forms for simplicity. Number one, Gauss's law for electric fields. First, recall that an electric charge creates an electric field, which then exerts an electric force on other electrically charged particles. Formally, Gauss's law states this: electric charges produce an electric field, and the flux of that field passing through any closed surface is proportional to the total charge contained within that surface. So Gauss's law for electric charge completely describes the electric field around any static charge distribution. If the math is too hard, that's okay. Remember that the electric field strength visually is proportional to the density of electric field lines, like these images here. The more densely the flux lines are arranged, the greater the intensity or strength of the field. Remember these 2 points from our water flow analogy. Remember, flux equals flow. More lines is like greater water pressure. Think of a strong fire hose versus a weaker garden hose. And lines pointing out are like a faucet or a hose or a source, and lines pointing in are like a sink or a drain. Only instead of water pressure, it is electric force pressure, but interestingly, the equations are very similar. Maxwell's second equation is also a form of Gauss's law, but in this case with magnetic flux instead of electric flux. So Gauss's law for magnetism states this: the total magnetic flux passing through any closed surface equals zero. What this means is there are no magnetic monopoles, or stated another way, there are no magnetic charges like positive and negative electric charge. There are no sources or sinks. You cannot isolate a north or south pole. They always appear in pairs, where you can isolate positive and negative charges. Magnetic field lines don't begin or end. They form closed loops, which means they cannot be shielded like electric charges or absorbed or reflected like light or electromagnetic radiation. It is this property that allows static magnetic fields and time-varying magnetic fields, or PEMFs, to penetrate deeper and work better therapeutically than any other form of energy medicine like electric currents, electric fields, light therapy, etc. Maxwell's third equation is Faraday's law of induction. Remember from Module 6 we saw that Faraday's law of induction says that a changing magnetic field will induce an EMF, an electromotive force, in a loop of wire, which then drives the current in that wire. Maxwell made the assumption that this electric field is present even without the conducting loop of wire. That is to say, there is still an electric field circulating from a changing magnetic field. So Maxwell's version of Faraday's law is more general and says that the EMF is equal to the line integral of an electric field over any closed loop, whether there's wire or not. That is, a changing magnetic field induces a circulating electric field, and this circulating electric field is the source of the EMF in any circuit, but it can also stand alone in space as a circulating electric field. Now, this is also called an eddy current, which means eddy means spinning, twisting, vortexing, and the direction of this circulating EMF opposes the change per Lenz's law. Remember the negative sign in Faraday's law. So this third equation of Maxwell's is really Faraday's law of induction, and it includes Lenz's law. It's just kind of a little more generalized form than we saw in video 6. Now, a PEMF note. All PEMF devices operate and affect the cells based on Faraday's law of induction. In fact, Faraday's law of induction is really the driving force of PEMF devices. The faster the magnetic flux changes, which remember we saw means a greater dB/dt or a greater flux per unit time, the larger the magnitude of the circulation of this induced electric field in your tissues. And this gives rise to ion transport, charge separation, energy production, improved microcirculation, and a lot of the benefits that come from PEMF therapy at the cellular level. It is this rapid rise and fall in the signal of the PEMF device, along with the frequency spectrum of the PEMF signal, which gives rise to frequency resonances at the cellular level, that is the most important thing when it comes to a PEMF device, not intensity. You do not need high intensity, as we've talked about in this course. So I just want to make a note that high intensity PEMF devices that use anywhere from 0.1 to 3 Tesla, which is about 1,000 to 30,000 Gauss of intensity, will create circulating eddy currents in your body that are way too strong, kind of like a category 3, 4, or 5 hurricane. And that's a good analogy because hurricanes are also eddy or circulating movements. So you do not want a super strong eddy current at the cellular level because that can damage the cells long term. Yes, your body and your cells can handle it short term, but it's not something you want to be using every day. And it is the physics of this that led the ICNIRP, or the International Commission of Non-Ionizing Radiation Protection, to give very clear-cut guidelines as to what are safe levels for PEMFs, or time-varying magnetic fields. I'm going to go through this in another video, but basically these high-intensity units are way off in the deep end, in the danger zone. Okay, this is again physics and biophysics, and it's a lot of really good experiments and testing done by one of the most respected governing agencies in the world that kind of governs the safety of electromagnetic and electromagnetic fields in the workplace and at home. More on that later. Maxwell's fourth and final equation is Ampere's law with Maxwell's displacement current, which says this. It says that moving charges like an electric current in a wire produce a magnetic field, just like we saw in module number 5. And of course, this includes permanent magnets, which are also a result of moving charges at the atomic level. Now, in addition to moving charges, a changing electric field can also produce a magnetic field. And this is something new, and it's called Maxwell's displacement current. So more formally, the Ampere-Maxwell law, which is the final Maxwell equation, in its integral form states this: the electric current, or changing electric field flux through a surface, produces a circulating magnetic field around any path that bounds that surface. This fourth and final equation is the one Maxwell made the most tweaks to in order to make it applicable to all electromagnetic phenomena. Now, Maxwell's first and second equations were very similar. Remember, Gauss's law for electric fields and Gauss's law for magnetic fields. So Maxwell knew there must be something complementary to Faraday's law. After all, if a changing magnetic flux produces an electric field, why is there not a complementary law saying the reverse, that a changing electric field produces a magnetic field? And indeed it does. So this was, again, a new discovery of Maxwell. So now let's behold these marvelous equations one last time. Really soak them in your subconscious and wonder at the beauty and symmetry in nature. If this is the first time you have seen Maxwell's equations, remember this day. These four equations together, along with the Lorentz force law, summarize the entirety of classical electrodynamics, which really does govern just about everything electrical and magnetic, including all energy medicine devices. Now, with the addition Maxwell made to Ampere's law, the equations were complete. And from them, we see a pattern in the production of both electric and magnetic fields, and how the two are connected, which was something that was not known before Maxwell. That is, if a changing electric field is generated, then a magnetic field is induced, which results in a changing magnetic field that induces an electric field. And this cycle continues. And guess what that leads to is light. Light comes from this interplay between changing electric fields and changing magnetic fields. That is, Faraday's law and Ampere's law go back and forth, kind of like you can take a slinky in your hand going back and forth. And this back and forth induction is what creates light. And it is the reason that light can be transmitted literally even like 13 billion light years through space from almost the beginning of the universe, because it just keeps recreating itself. So we'll look more at light next in part 2 of this module. So thank you for watching, and stay tuned in part 2 where we're going to look at how light really comes from Maxwell's equations, which we just hinted at, and then we're going to go through all the different forms of energy medicine and how they're related and how they're different within electromagnetic field theory.